So if you've built or want to build AI applications, chances are you're familiar with vectors. And if not, this is the video for you. In this tutorial, we'll be walking through creating a MongoDB vector search index, indexing data, building a pipeline, and integrating it into your application. Now, if you already know what a vector is, skip this next couple of minutes, but real quick, we'll explain what a vector is and how it's used in an AI application. So let's say you're building a fruit application, a fruit AI application, and we have users that are first inserting different types of fruit. Let's say we've got an apple, we've got a banana, and we've got an orange. Each of these fruits needs to be encoded by a model into a vector. So we send all of these to a model. And we'll explain how all of this looks like in code. But we have that model return an embedding, and an embedding is just an array of floats of different lengths. And then that embedding gets inserted into a vector store. And most vector stores use the same underlying data structure. It's called HNSW, Hierarchical Navigable Small World Graphs. I know that's a mouthful, but it is a core data structure in most, if not all, vector databases. But here we'll just be using Mongo. It abstracts a lot of that. So let's say we've already indexed and stored all of these different fruits. And let's say we have another user that wants to find the most similar fruit to an image that they provide. Let's say they're providing grapes. These are my grapes. And these grapes get sent through that same model. And this is very important. It has to be the same model with the same number of what's called dimensions. And we'll explain that in a bit. That model then also returns an array of floats. And then you send that array of floats through what's called a KNN operator. And KNN stands for K nearest neighbor. So it finds all of these similar arrays of floats based off of what is already in the HNSW, and it returns the top K results. So the most similar arrays of floats based off of what is already in the HNSW data store. So that is the TLDR of a vector search database. Obviously it gets more complicated, but for this video, because we're only doing this in a short amount of time, that is the extent of what we'll be explaining for as far as the fundamentals go. So let's get into actually building the vector search index. But first things first, we need to select which model we want to use. And Hugging Face has a huge selection of sentence transformer models. We'll be using the most popular one. So let's say we go into the models list and let's go through the sentence transformers, sentence similarity transformers. And we can see what the top, most downloads are. And it looks like all MPNet base v2 and all mini LLM L6 are the two most popular. So let's see this one. It looks like it has 768 dimensions. And a dimension is just how many of those floats are in the array that we then store in the HNSW. So it seems we have 768 dimensions in this one. And then for the other one, we have 384 dimensions. So when we go ahead and build the search index, we need to ensure that we're providing that dimension count in the embedding, in the index that we're creating. So in the Atlas Search UI, we already have a database. And let's say we have a collection already specified, and I'm just using the sample loaded data set. When you create a cluster, you have the option of loading a sample data set. And we're just going to use the sample mflex database, and we'll use embedded movies. And the default embedded movies collection already actually has a different embedding array, and it uses, I think it's like 1500 dimensions. It uses the OpenAI embedding model, and we won't be using that. It's too expensive, too slow. So we'll just be doing this locally. Again, we've got this sentence transformer model that we'll be using. It's got 384 dimensions, and we can see how to use it. One line of code, model.encode the array of strings that we'll be using. So we can go ahead and create the index. I've already created it, actually, but we can see what's happening here. We've got dynamic true, which just means that we're indexing all of the fields in the collection using what's called a TF-IDF index, a term frequency over the inverse of the document frequency. We don't need to know that for this, but what this allows is for us to be able to do what's called hybrid search. So searching across both text and vectors in the same query. That's out of scope for this video, but we'll be doing that in a separate one. So we've got that dynamic true enabled, and then we also have the fields that will be specified in this index. And we have two different fields here. One is plot embedding 384, in which we're saying the dimensions for this vector is 384 dimensions. And then we have another one that is 768. And the reason that we're doing both is we want to actually compare the results across both of these different embedding models. This is really important when you're evaluating different models against whatever acceptance criteria that you have in your application. Right? And we're calling this default. So let's go into our code. In our code, I'm deciding to use the mini LLM L6v2 sentence transformer. And I already know, because I'm familiar with this, and we just looked at the Hugging Face page, that it has 368 dimensions. So we'll be using, 368. So we'll be using inserting the embeddings using model.encode into this new field that we've created called plot embedding 368. And so what we're doing in this code is we're just iterating through every document in the collection, encoding it, and inserting a new field into that document. So let's save that, and we can just do a quick run. And I believe all it's going to do is print out the titles of each of them as they become embedded. So wait a couple seconds, and that's what's happening here. It's embedding I believe we're using the plot. Yeah, we're embedding the plot string of every movie into its corresponding document. So we see the plot here is a string, and we are embedding that into this array of floats. And again, this is 384 dimensions. And this is, again, important because that is the field that we can then use once we do the KNN search later on. So we have that field, and now what we could do is, again, we could stop running that because I've already actually indexed it. So we've indexed the data, and now it's time to integrate it. So let's go into the Nux AI panel. And what we can do is specify the model that we want to use when we do this aggregation query. And since we used the mini LLM model before, we'll be doing that. We've got our connection string, sample mflix as the database, and embedded movies as the collection. And we're using the default index here, same index, and we're querying the plot embedding 384. So as you recall, we have that plot embedding 384. And then we're limiting the results to 10. And then we only want to return the plot. And the query that we're embedding is story about soldiers in WW2, World War II, Japan. So let's run that. And we can see all of the plots that are returned. And obviously, as you can see, this isn't an exact text match. And that's because we're using k-nearest neighbors. We're finding the similar embeddings of what we already have in the database against what we're sending to this query pipeline. And we can see how long that took 1 second. This is milliseconds. And that's the 384 dimension query. And again, we use the sentence transformer mini LLM L6, but let's say we want to compare that against a different one. We want to compare it against this model, which is 768. Now, if I hadn't already done it, I would have to use that model here. I'd have to I'd have to change the string and then insert it into a new field, and then just double check that I have that index already specified in my index definition, but I've already done all that. So now what we can do is go to this next block here and use that other path. And we have the same query here, and it's just running it through a different embedding model, the MPNet base v2 embedding model, as we indicated in our code and the Hugging Face website. So we can run it. And again, it's doing the same thing. And we can actually see the results are different. It's querying the same collection. So let's just double check it's querying the same collection, embedded movies, albeit a different path. And that different path is, again, the different embedding space of that plot of the same movie. And so we can see that we're actually getting different results here. And let's do this real quick. Let's actually grab the title as well. Let's return the title. That way we can actually compare the movie names, the Pacific, and let's do it up here too. And this just helps us really quickly see how the results compare. And that looks right. Okay. To End All Wars is the first one, followed by the Pacific. And here, the Pacific is first, Fighter in the Wind. To End All Wars is third. And the reason for this difference is these two different embedding models were actually trained on different corpuses of data. Usually it says it at the very bottom, pre-training. So they have a pre-trained model here that they use, and looks like they fine-tuned it using different sentence pairs. And we could see the mini LLM, I think it was trained on, let's say pre-trained on this model, which is pre-trained on another model. So like all of these models were kind of pre-trained and fine-tuned under the same foundational model. If you've ever heard the term foundation model, the foundation model is like the core building block, and people are basically fine-tuning models on top of that. And looks like BERT base might be that foundation model here, and we have that research paper that was used to construct it. So we have these different embedding models and their corresponding queries that we have here that we're presenting in this UI. So what do we do now? Well, we can actually combine the output of that into an LLM. So let's say in this LLM, we want to say, we want it to generate a movie title from the array of plots and titles. So what we're saying here is come up with a movie name that encompasses all of the plots in this array of objects. So we're saying blocks.indexString, and indexString is the name of this cell here. So we're sending the outputs of this query into the context of this GPT model. And I believe we're using GPT 3.5, but we could use any of these other models, modify the temperature, max tokens, et cetera, et cetera. And then we're using a JSON function to ensure that the output adheres to this JSON structure. So we're saying this JSON structure, it has to return a movie title key, which has this description. And this description is really just the instructions that we're telling the GPT model to run through. And under the hood, we're just using an open source library to force the input into this JSON output. And this is what allows us to integrate this into an API. So let's run all of these real quick. And again, it's running through each of these queries. We've got all of them. And then we've got the output, movie title, War Chronicles. And I'm pretty sure that doesn't exist at all here. So it completely fabricated this movie. And we can actually have a new field here, so like explanation, and just tell the model, like, explain why you decided to create this movie name. And then we can save it. Let's refresh the page just so that we can clear out all the outputs, and then let's run it again. We got this output, we got this output. Now we're waiting for the GPT model to complete. Oh, nice. Yeah, and so it has the explanation of why it decided to come up with the movie title War Chronicles. Right, so we've kind of experimented and modified our pipeline, which is really just two different queries. And let's actually, we're using two different queries, and we're sending just one of those to this GPT model. And in a production environment, we want to minimize the number of blocks that we have in this pipeline, just so that it's fast and reliable and durable, etc. But let's actually dive into calling this workbook in Nux via an API. So let's go into Postman, and we want to. I'm actually modifying the query. I'm saying I just watched Life of Pi, so we'll say a story about a young man and a tiger on a ship in the middle of the ocean. And this is calling this API. And what this allows us to do is integrate that workbook that we just constructed into our application via a single API call. So let's run that. And again, it's running through those three blocks that we've created in that Nux workbook. Block 1 was that first query, block 2 was the second query, and block 3 was that GPT 3.5 turbo model. And each of them are going to return those outputs as well as metadata for all of them. And so we could see Life of Pi, as we can guess, is that first result. And then we've got a bunch of others that all are somewhat relevant to the query string that we've specified. So that was actually the first model, or the first query using that model. And this is the second query using the second model. Again, both different dimensions, different encoders, etc. And then we could see the GPT model came up with a completely different movie title and explanation of why it decided to do that. So that's the end-to-end walkthrough of building a MongoDB vector search index, experimenting with it, combining it with an LLM, and integrating it into your application. And we can do so much more with different models, data, and code. We can combine a different, like DALL-E, and actually generate an image from one of these outputs. We can do some different pandas or scikit or scipy, or all of the different Python libraries that we want to combine with these different blocks in a pipeline. And once we're happy with it, we can productionize it, deploy it, and call it via an API. So if you need any help with developing, evaluating, or deploying MongoDB, or really any AI pipeline, reach out. We would love to help you. And I'll share a link to all of the resources that we used in this tutorial. Let me know if you have any questions. Thank you.